So tertiary alcohol, that's going to lead to elimination. So here you're going to get the alcohol back, and then you're going to get this elimination. You're going to get the leaving group, and then the other product of this reaction will be the elimination product, which in this case will be ethene. All right, so that's why the alcohol must be primary or secondary, otherwise it's too bulky to function as the nucleophile in the SN2. So that's one limitation. Now, okay, let's see. Is it possible to leave the lights on? Well, but if I leave the lights on, then I don't think the image is going to be very, I think it's going to be fuzzier. See, that's the lights on. Want to try it this way? Whoever sent me that message, you want to try it this way? Okay. Your wish is my command. Okay, so we saw that the alcohol can't be, in general, can't be tertiary, but remember that the alcohol can't be tertiary because then we're going to get elimination. But if the alkyl halide can't undergo elimination, then the alcohol could be tertiary. For example, if we were to start out with that same bad tertiary alcohol and react that with sodium hydride and get this, and now if the alkyl halide is this benzyl halide, then even though we can't have this, even though this tertiary alcohol is ordinarily no good, this guy can't undergo elimination because the elimination product, so this Williamson is going to work out pretty well because this guy can't eliminate. Elimination puts in a new double bond between the alpha carbon and the beta carbon. The elimination product would be something like this. That would be the elimination product, and we see a carbon atom with 5 bonds. So this guy here can't exist, right? That's the alpha carbon, there's the beta carbon. So this thing can't eliminate. So under special circumstances, when the alkyl halide can't undergo elimination, then a tertiary alcohol is okay, but that's just, you know, a very narrow scope. Okay, so that's one of the problems with the one of the limitations of the Williamson. The other limitation is that the alkyl halide has to be primary, and if it isn't primary, then what we're going to get is elimination. So, for example, we're still talking about the limitations of Williamson. The alkyl halide must be primary. And what happens if it isn't primary? You're going to get elimination. So it's going to be, see, so there's a primary alcohol, that's okay. We react that with sodium hydride, we get this alkoxide, but now let's feed that some secondary alkyl halide. Well, now the secondary the secondary center is now just too crowded. And this guy, he's a nucleophile, but he's also a base. And so what this guy is going to do is promote an elimination anyway. So we get the proton slammed back on. We get Br minus, that was the leaving group. And the other product of this reaction will be an alkene. So that's going to be an E2 elimination product. So those are the big limitations. So one of the upshot of what I'm talking about is that some ethers can be created by Williamson ether synthesis, but some cannot. Not every ether can be made using a Williamson reaction. Okay, so let's look at some practical examples. All right, so let's see, is this gonna work? Okay, so just bear with me here once again. Okay, bear with me. Man, tell you though. All right. Okay, so here's an ether. It is the compound that is responsible for the delightful aroma of the wallflower. And so maybe we're used to thinking about a wallflower in the sense of someone who gets all dressed up to go to the big party, but no one asks them to dance. So I guess that's what has happened to this lady here. And so this is the wallflower, and this ether can be synthesized using Williamson. All right. And so we see that this wallflower ether can be made in two different ways using a Williamson ether synthesis. Is that the Williamson ether synthesis creates the carbon-oxygen bond to the left of the ether oxygen, and it could create the bond to the right of the ether oxygen. So many ethers can be synthesized in two ways using using Williamson technology. So I'm going to call this route A. I'm going to call this route B, and I'm going to see how I could create this ether in two different ways using Williamson. Okay, so route A would be, I would start with this alcohol, right? I'm going to make this bond that I've labeled A. I'm going to start with this alcohol and react that with sodium hydride. And that makes this alkoxide. And now I can bring in, sorry. I'm still very flummoxed by all of the problems I have to deal with here. Try again. Route A. I'm going to make this carbon-oxygen bond here. So I'm starting out with this alcohol, and I'm going to react that with sodium hydride, and I get this alkoxide. And now I can bring in the rest of the molecule with this benzyl bromide. And so this nucleophile is going to attack this carbon. It's going to kick out Br as a leaving group. And that is one way of making this wallflower ether. Okay, so in Williamson, I can create the carbon-oxygen bond to the left of the ether oxygen, and I can create the carbon-oxygen bond to the right of the ether oxygen. Okay, so the other technique here could be, now I'm going to make this bond be here. So I would start out with this alcohol. It's primary, it's okay, alcohol was primary, they're both okay. And so now add sodium hydride, and that makes this. And now bring in the rest of the molecule, which is going to be this primary alkyl halide over here. So I get the very same wallflower ether. Okay, so what I'm trying to say here is that many ethers can be created in two ways using Williamson. You are making the carbon-oxygen bond to the left of the ether oxygen, or the carbon-oxygen bond to the right of the ether oxygen, and many ethers can be made in both ways, but not everyone, but not all of the ethers. So let's look at some further examples. What about we're trying to make this ether? Okay, so we could make either this bond over here, call that A, or we could make this bond over here, call that B. So tell me in the chat, will A work and B work? Or will only A work, or will only B work? So let's try to guess here. Is A going to succeed? Is B going to succeed? Will only A work, or will only B work? Okay, so I see a lot of people have a lot of opinions. So your menu of choices are A only, B only, or both A and B, or neither A and B. So you have four choices, right? A only, B only, A and B both will work, or neither A nor B will work. Okay, so I see a lot of opinions about a lot of stuff. So B only. Okay, so let's look at A, right? A is going to be a dismal flop. A is going to be a dismal failure. Let's see why. So we're creating the bond, we're creating this carbon-oxygen bond. So that means that we would start with this alcohol. It's primary, so far so good. And then react that with sodium hydride. We get this alkoxide. And now bring in the other side of the molecule. And so that would be that, and just put a halide here, maybe Br. Okay, no good. Why? Tell me in the chat. Tertiary, no. Yeah, so this reaction is going to be no good. How come? Well, it has nothing to do with being primary, secondary, or tertiary. It has nothing to do with elimination. It has nothing to do with being bulky. Okay. All right. Ooh, some creative reasoning here. I like it. No good. Why? Because this is supposed to be an SN2 reaction. And one of the things that we know about SN2 is that the carbon that bears the leaving group must be sp3 hybridized. This guy is sp2 hybridized, and it has to be sp3 for SN2. So that's why this reaction's no good, because the hybridization state of the carbon is wrong. What do we know about SN2 is the nucleophile has to attack in a backside manner. It can't come in at an angle from the front, from the top. It can't come in from an angle from the bottom. It has to do a backside attack. So in order for SN2 to happen on this sp2 hybridized carbon, what would have to happen is something like this. There would be the benzene ring, there would be the Br, and somehow the O- would have to stick its head somehow in the middle of this ring in order to attack in its backside way. It would be kind of like you thrusting your head through a manhole cover, right? So the hybridization state of that carbon atom is wrong. SN1, SN2, E1 and E2, all of those can only happen when the leaving group is on an sp3 hybridized carbon and never anything else, right? So that's no good. Route A is no good because the leaving group is on the wrong hybridization state. Okay, so is B any good? Let's try that. Okay, so that would mean starting with this alcohol. Right? This is phenol. This is a special kind of alcohol. If we want to think of it as secondary, we can. React that with sodium hydride. That's overkill in this case, but that's all right. We get this phenoxide. And now attack the primary alkyl halide. So that's going to work okay. Check. All right, so that's a Williamson that works in one direction and a Williamson that doesn't work in another direction. Okay, so let's see. Let's try this again with another system, and let's see whether both will work, one will work, or neither will work. All right, what about this ether? We could create this bond A, or we could create this bond B. So tell me in the chat, is A gonna work? Is B gonna work? Will they both work or neither of them work? A good. Your choices are A only, B only, A and B both good, or A and B both bad. Okay, in this case, B only. B only. All right, so let's look at A, and let's see why this is not going to be any good. All right, so that means we would start out with this alcohol, methanol, react that with sodium hydride, and so we get this methoxide, and now react that with the with this. No Williamson. How come? Tell me in the chat. Why isn't this any good? Yeah, the substrate is tertiary, right? And so our restriction on the alkyl halide is that it must be primary, right? So this guy here was tertiary. It's going to give elimination. The actual product here is going to be the elimination product, where that proton just gets put right back on and we get this elimination product. Yeah, so A is no good because the Williamson is an SN2 reaction and elimination is the enemy of substitution. Okay, so now B, let's look at B, creating this bond B. So that would mean you're starting with this tertiary alcohol, and we just said that in general, the tertiary alcohol is not going to work. React that with sodium hydride. We get that, and now bring in the methyl group. Oh, that's going to succeed brilliantly. That's going to be very good. Even though this is tertiary, this is going to work. So tell me in the chat why it works. Right, it looks like we've just broken all the rules of Williamson, right? We have a tertiary alcohol. Why does this work? Anybody want to give it a shot? Can the substrate be secondary? No. Well, you know, there are always exceptions, but in general, no. So why does this work? Why is this okay? Because this thing can't eliminate. Elimination sets up a new double bond between the alpha carbon and the beta carbon. That means, that presupposes that the molecule has two carbons in it. This guy doesn't, right? This is the alpha carbon. That's the carbon that bears the leaving group. Where's the beta carbon? Where am I going to draw a double bond from this carbon to another carbon? Elimination is the enemy of substitution. Elimination is the enemy of Williamson. But this methyl iodide doesn't have a second carbon. It can't eliminate so that the substitution will work. Yes, so you're getting the hang of it? One more. What about this ether? Is that going to be we could create bond A here, or we could create bond B here. So tell me in the chat, will A work? A only, B only, both A and B are good, or both A and B are bad? Yeah, both are bad. This is an example of an ether that cannot be made by Williamson. Okay, so let's go through that. A, creating bond A, That would mean starting with this alcohol, reacting it with sodium hydride in the first step, and then reacting it with this tertiary alkyl halide. No good. No Williamson. Why? This guy is tertiary. We're going to get elimination. No Williamson gives E2 elimination. Okay, so that's no good. What about B? Creating bond B. That would mean starting with a tertiary alcohol, reacting that with sodium hydride to make the alkoxide, and then reaction with this secondary alkyl halide. Once again, same thing. No Williamson. It's going to give an E2 elimination product because this is going to be a very sterically hindered base. It can't get in here into this secondary substrate to push the leaving group out. So someone asked me in the chat whether a secondary alkyl halide could be used here. Well, I can engineer a secondary alkyl halide that cannot undergo elimination and will therefore work in a Williamson. But you know, this is a freak show, right? Something like this. Benzene ring over here, benzene ring over here. Put the alkyl halide there. That can't undergo elimination. I can't put a double bond to this benzene ring on the left. I can't put a double bond to this benzene ring on the right. So can some secondary substrates undergo Williamson? Well, they can, but it's very limited number. It's in general not a procedure, not a good idea to use a secondary alkyl halide, but I can think of some that could undergo the reaction. Okay, so now I'm going to switch gears and go into a totally different family of reactions. So let me see, any questions about Williamson in the chat before I move on to something else? Any questions about Williamson in the chat that we could entertain? Because we're going to move into something else. Oh, there are many weird exceptions. All you're looking for is something that cannot eliminate. What else? No? Okay. All right, so the of alcohols. Now, let's review some of the concepts of oxidation and reduction that we learned in Gen Chem. And that will give us a nice background for understanding some of the chemistry we're about to talk about. So let's review oxidation and reduction, which is what we learned about, which maybe we covered in Gen Chem. Okay, oxidation is defined as the loss of electrons, Right, so maybe that's what they told you in Gen Chem that oxidation was, the loss of electrons. But that does very little good for us here in organic chemistry. So this is something that's much more appropriate to in Gen Chem. When we're talking about oxidation of an organic molecule, what we're really looking for, the hallmark of oxidation for an organic compound, yes, it's the loss of electrons that does us very little good here. But what we're really looking for is an increase in the number of bonds to oxygen. Oh, that makes sense, right? That's why they call it oxidation, because what's going to happen when an organic molecule undergoes oxidation is that the number of bonds to oxygen is going to increase, not necessarily the number of oxygen atoms, but rather the number of bonds to oxygen. Another hallmark of oxidation is a decrease in the number of bonds to hydrogen. Right, so that's another signal that something has undergone oxidation, of an organic molecule has undergone oxidation. Okay, so let's look at some examples of oxidation, and then we'll go through all of that same thing for reduction. Oh no, let's do this. Let's do reduction. Reduction. In Gen Chem, they told you that reduction is the gain of electrons. Well, that's very nice when you're talking about the zinc ion or the gold ion or something like that, but those aren't organic. In organic chemistry, one of the signals, one of the signposts of oxidation is an increase in the number of bonds to hydrogen, or a decrease in the number of bonds to oxygen. Right, so it's exactly the reverse of what we are looking for in oxidation. Increase in the number of bonds to hydrogen, or a decrease in the number of bonds to oxygen. So this is how we can tell in a quick and dirty way whether oxidation or reduction has happened. Okay, so for example, something like this. Okay, let's go to a new slide. Go to something like this. If we start out with methane and convert that to carbon dioxide, oh, that's an oxidation, right? Because we have, this is an oxidation because that carbon atom is gaining. It started out with 0 bonds to oxygen, and now it has 4 bonds to oxygen because this is 2 carbon-oxygen double bonds. So that's an oxidation. And if we went through all of the electron bookkeeping, we would see that indeed this carbon atom is losing electrons. This is carbon in the -4 oxidation state. This is carbon in the +4 oxidation state. So it has lost it has lost 8 electrons. That's an oxidation. But what we're really looking for is an increase in the number of bonds to oxygen. Okay, so something like this. Is that an oxidation or a reduction? Oh, that's another oxidation. where this carbon atom starts life with 2 bonds to oxygen, and now it has 3 bonds to oxygen. So that's an oxidation. Something like this reaction here, which maybe you saw in Orgo 1, you take cyclohexene and convert it to cyclohexane. Is that an oxidation or a reduction? Oh, that's a reduction, because this carbon starts life, both of those carbons have 1 bond to hydrogen, and now in the product, they have 2 bonds to hydrogen. So that's a reduction, an increase in the number of bonds to hydrogen. So that's the first thing we want to say about oxidation and reduction, is that this is how we can tell whether oxidation or reduction have happened. Okay, so continuing our little review of oxidation and reduction concepts. Now, do you guys remember the table of oxidation and reduction potentials? Remember that? And it was a big table that it was a bunch of half reactions, and you probably in Gen Chem did all kinds of stuff with that. Well, we're going to do all kinds of stuff with that now. So it would be a waste to throw away all of that great chemistry that you learned in that you learned in Gen Chem. So now what we're going to talk about is the thermodynamics of oxidation and reduction, which is conflated in this term called redox. Okay, so recall the standard reduction potential table. Right? You remember that from Gen Chem. Okay, so let's look at an inorganic example to start off with. No, we don't have time. So let's look at something that has organic chemistry in it as well. So I looked up that standard reduction potential, and I see copper 2+ plus an electron going to copper 1+. And the standard reduction potential, E0, for this is positive 0.15 volt. So am I jogging your memory? Are you remembering stuff that looks like this? Okay, and so now we can throw in some organic compounds, an organic compound. So this is acetone plus 2 protons plus 2 electrons, and this is going to isopropyl alcohol, and the E0 for this reaction is positive 0.12 volt. Okay, one more. Zinc 2+ plus 2 electrons, and that's going to zinc metal, and the standard reduction potential for that is minus 0.76 volt. Okay, so here's my question for you. All right, so let's just see if we can keep that here on our screen somehow. Let's keep those numbers up there somehow. What can reduce a ketone to an alcohol? Right, and here's your menu of choices. Copper 2+, copper plus, zinc 2+, or zinc metal. right? I'm trying to remind you of how to use this standard reduction potential, which undoubtedly, or I hope you saw in Gen Chem. So let's see who remembers Gen Chem. Yes? So there are your choices. What can reduce, right? Because this ketone to an alcohol, that's a reduction. This carbon atom starts life with 2 bonds to oxygen. Now it just has 1. This carbon atom starts out with 0 bonds to hydrogen. Now it has 1. That's a reduction, right? That's how we tell whether an oxidation or reduction has happened in organic chemistry. So here are your menu of choices, right? Who remembers Gen Chem? Who remembers how to use these standard redox potential data? Tell me in the chat. Here are your 4 menu choices. Anyone want to give it a shot? Okay, ooh, I see a lot of opinions. Someone told me copper, but I see two copper species here. I see copper 2+ and copper 1+. So which copper do you mean? Okay, the correct answer, zinc. Okay, that's the only thing that's up here that can reduce. Okay, so let's go through how you use, let's remind ourselves how we use these standard reduction potential data. Okay, so we want to go from the ketone to the alcohol. That's the reduction, and it has this this value here. Okay, so what we do is we choose the is that we want this reaction to happen as written, and so we must pair this half reaction with another half reaction which is going to be less positive, and we reverse it, right? So this reaction here would be paired with this one because this reduction potential is less positive, but because that's a reduction and that's a reduction, because all of these are reductions, we have to have an oxidation if we have a reduction. We can't have 2 reductions. We have to have an oxidation and a reduction. So we choose this guy here whose number is less positive, and we reverse it. It will happen this will happen as the reduction, and this will happen as the oxidation. Okay, so the reaction that we want to happen is the ketone plus zinc metal plus 2 protons going to the alcohol plus zinc 2+, right? And the overall reduction potential for this whole system is going to be the more positive guy, the more positive E0 minus the less positive E0. So the more positive E0 is plus 1.2 volt. The less positive one is a minus of a minus 0.76. And so that adds up to plus 0.88 volt. And we want E0 to be a positive number because, remember this equation, delta G standard is equal to minus NFE standard. And for the reaction to be spontaneous, delta G has to be negative, and if E0 is also negative, delta G will be positive. So we want E0 to be positive so that delta G can be negative. Remember all of that stuff from Gen Chem? Okay, well, I wouldn't blame you if you were fuzzy on that, but we're going to try to bring ourselves back up to speed. Okay, so now let's try this again. Let's bring our data table back. Let's bring our data table back. And now what I want to ask you, right? So let's just get some more practice in using these this Gen Chem concepts. What can oxidize the alcohol to the ketone, right? And that's an oxidation, because this carbon atom starts life with 1 bond to oxygen. It finishes up with 2 bonds to oxygen. That's one of the hallmarks of oxidation. So here again are your choices: copper 2+, copper plus, zinc 2+, and zinc metal. Okay, so you're looking at all the data, you're looking at your menu of choices. Tell me in the chat, what can oxidize the alcohol to a ketone? All right, now someone told me copper, but you have to tell me whether it's copper plus or copper 2+ or what. Yeah, it's going to be copper 2+. Yeah, it's going to be this one. And guess what? That's what you're doing in one of your labs. You're going to use copper 2+ to oxidize an alcohol to a ketone. Okay, so let's try to go through and explain how we came up with all of that. Okay, so here we want, see this reaction here? This says the ketone is the starting material and the alcohol is the product. That's not what we want. We want the reverse. We want the alcohol as the starting material, and we want the ketone as the product, right? Because we're asking ourselves, what can oxidize? So this guy has to be reversed. It has to be the oxidation. It must be paired with a reduction reaction which has a more positive E0. In other words, this one. So that one will happen as a reduction. This one with the more positive E0 will happen as written. This guy, will have to be reversed. That's the reaction that we want to happen. Okay, so we want that going to this. So we must reverse this guy. So our balanced equation is going to be, it's going to be balanced. It's going to be the alcohol as the starting material plus copper 2+, because that's the reaction that had a more, we reverse this one, we have to pair it with something that has a more positive E0, going to the ketone, which we want, plus copper plus H plus. And the reduction, the overall reduction is going to be the more positive guy that happened as a reduction. That's +1,5, minus the less positive guy. That's going to be this one. And this works out to a positive 0.03 volt. And as we said before, because of delta G is equal to minus NF delta E, we want E0, we want E0 to be positive. Okay, so where do the electrons go? Don't quite understand your question. The electrons, see, this is an oxidation. This is an oxidation. This is a loss of electrons. This guy is losing electrons. Who is picking up the electrons? Copper 2 plus, right? Copper 2 plus is becoming copper 1 so that it is absorbing an electron. Is that what you wanted to know? Okay, what else? Okay, I'll entertain some questions here because this is a review of stuff you were supposed to have learned in Gen Chem. Why is it not 2 copper 2 plus? Well, this equation that I've written here is perfectly balanced, right? Because if you want other kinds of copper here, you're going to get, it's not going to be a balanced reaction. Back to Gen Chem, right? I'm going to reverse this guy, and then I'm going to combine these two. And in the balancing procedure, I have to multiply this equation by 2. So it's 2 copper 2 plus. Whoa. Uh-oh. Sorry about that. 2 copper 2 plus. Sorry about that. My bad. So did that fix anything? Okay, so you use the +2,5 value even when we run the reaction backwards. We do, right? So forget about what they told you in Gen Chem. This is how you do it. The more positive minus the less positive. Right? Forget about what they told you in Gen Chem. The more positive number minus the less positive number. Right? That's just the simplest way of expressing what you're supposed to do. I know your Gen Chem professors probably said the negative of the negative of the negative, or the positive of the negative, or something like that. That's so hard to remember. No, we don't multiply the E zeros by 2 because all of that multiplication is already built into that number. Okay. So look at my lecture notes online, and there are more problems. There are more problems where you're getting a workout with those oxidation, manipulating those oxidation numbers. So what we've just been talking about is oxidation and reduction, how we know that oxidation or reduction has happened, and when is oxidation or reduction possible, right? We know that oxidation and reduction happened when there's an increase in the number of bonds to oxygen or to hydrogen, or a decrease in the number of those bonds. That's how we know oxidation or reduction has happened. And how do we know when those oxidation or reduction reactions are possible? That's where we have to go to that table. That's where we have to go to those tables and be able to identify what can oxidize what can reduce what. Okay. So with all of that out of the way, now we're ready to talk about our first oxidation and reduction, our first oxidation of an alcohol reaction, which is chromic acid. Is oxidation of alcohols using chromium 6 reagents, right? And we could also write this chromium 6 plus. All right. And so here's our overall reaction. If we start with a primary alcohol, react that with chromium trioxide, right? The Lewis structure of chromium trioxide is that. Oh, and we see that this chromium trioxide is highly, highly oxidized. Look at all of those bonds to oxygen, right? So it's very difficult to oxidize CrO3 because it's already in a very highly oxidized state. Okay, plus acid, and what we usually use is sulfuric acid. And then the solvents that we use here, water, right? That's going to dissolve up the chromium trioxide. The water, that's going to dissolve up the sulfuric acid, but not every alcohol will dissolve in water. So we usually need to have an organic solvent that can dissolve up the alcohol as well. So the solvent of choice here is acetone, right? These are solvents, right? So the product here is going to be this carbon. I'm going to put a dot on him. This carbon gets oxidized to a carboxylic acid. Is this an oxidation? Oh my heavens, yes, because that carbon with the dot went from having 1 bond to oxygen, now it has 3 bonds to oxygen. That carbon with the dot went from having 2 bonds to hydrogen to 0 bonds to hydrogen. And remember, that's what I said is one of our hallmarks of oxidation and of reduction, counting the number and the change in the number of bonds to oxygen or hydrogen. So this alcohol gets oxidized to the carboxylic acid if it's primary. Okay, so if it's a secondary alcohol, the same suite of reagents, chromium trioxide, sulfuric acid, water, acetone. Now the secondary alcohol is oxidized to a ketone, right? Not to a carboxylic acid, but rather to a ketone. So it's in an oxidation. Yep, this carbon with the dot starts life with 1 bond to oxygen. Now it has 2 bonds to oxygen. This carbon with the dot started out with 1 bond to hydrogen. Now it has 0 bonds to hydrogen. So that's all an oxidation. Okay, what if it's so notice that the carbon with the dot is gaining bonds to oxygen. That's how we recognize oxidation. So what if it's a tertiary alcohol? What if it's a tertiary alcohol? Something like that. And we add chromium trioxide, sulfuric acid, water, acetone. That carbon with the dot is going to gain bonds to oxygen. Tell me in the chat. Yeah, what's the mechanism? Give me a second, okay? We're getting there. Tell me in the chat what's going to happen. That carbon with the dot has to gain bonds to oxygen. What's going to happen? no reaction. RxN means reaction. Because for oxidation to happen, that carbon with the dot is going to have to gain a bond to oxygen. We can't have something like this. We can't have something like that, right? That's too many bonds to that carbon atom. So a tertiary alcohol cannot be oxidized cannot be oxidized using this chromium trioxide, sulfuric acid, and water and acetone system. So it's only going to be primary alcohols and secondary alcohols that are susceptible to oxidation and not a tertiary. Okay, so this complex of reagents here, this chromium trioxide, H2SO4, water, and acetone, this is called the Jones reagent, in honor of the fellow that discovered this combination sometime in the 1920s. All right, so and this reaction with chromium trioxide, sulfuric acid, water, and acetone, this is also called the Jones reaction. All right, so let's look at the mechanism of the reaction. Very lengthy, very complicated. And we have to break it down into what happens with a primary alcohol and what happens with a secondary alcohol. So let's look at Jones oxidation of a primary alcohol. And remember, this goes all the way to a carboxylic acid. All right, so here's our primary alcohol. There's the chromium trioxide. Now look at this combination of stuff and tell me who is the nucleophile and who is the electrophile, and how do you know? Who's the electrophile? He's easy to spot. Who's the electrophile, and how do you know he's the electrophile? Oh, the CR03, that is the electrophile, because you have that poor little tiny chromium atom that is bonded to all of this highly electronegative oxygen, sucking electrons away from that chromium. Yep, so this chromium atom, that's the electrophile. And the oxygen atom of the alcohol, that's the nucleophile. So the first step in this mechanism here is the attack of the nucleophilic oxygen on the chromium. This is nucleophile attacking electrophile. So we have a species that looks like this. Right, with a positive charge, positive charge there. And now what we get is a lot of fiddling and diddling with protons. So we have a base in the solution, and that base is water, or also the alcohol could function as a base. Or maybe this O- here of another molecule could function as a base. So now what we see here is a deprotonation, right? I'm picturing this proton just falling off of its own accord, but that's not what happens. A base comes along and removes that proton, but it could be water, it could be another molecule of alcohol, it could be a lot of stuff. So we're just picturing that proton is falling off. And so now we have a species that looks like this. But now that O minus up there, he's not very happy. We have sulfuric acid in the solution. We have sources of protons. So what happens next is that a proton goes on this oxygen atom up here. So these two steps we just talked about, this is just a lot of fiddling and diddling with protons. This proton falls off, it goes off into the solution, it's never heard from again, but there are a lot of protons in the solution. One of them comes back on here. And before I go any further, I want to make sure that you understand that if this proton is named Fred, this is not Fred here. This O minus doesn't wheel around and pick off this proton, because to do that would require a 4-membered ring transition state. And what do we know about 4-membered rings from Orgo 1? Very strained. To repeat, if this proton is Fred, this is not Fred here. This is Mary. This is Sally. This is somebody else. This proton went off into the solution and was never heard from again. But there are a lot of other protons in the solution. One of them came on here. Okay, so this thing is called a chromate ester. It's not really important what it's called, but that's a chromate ester. Okay, and so now we're ready for more steps. Okay, we have that water in the solution. We have a hydrogen. We have a hydrogen atom here on this primary primary carbon, and so this is really important. This is really the most important step of the mechanism here, is that the carbon atom, the alcoholic carbon, the carbon that originally had the OH group, it has a proton on it. This water comes in, removes that proton. The electrons rush in here. There's our new carbon-oxygen double bond, and this bond breaks in the direction of the chromium atom. Okay, so what we have here is, oh, there's an oxidation product. We've gone from something that has 1 bond to oxygen to something that has 2 bonds to oxygen. That would be an aldehyde in this case. The inorganic junk we don't care about would be hydronium ion, and this thing, and that thing, right? Now, this guy here, so that's hydronium ion. This guy here, by a very complicated mechanism that we're not going to get into, eventually turns into chromium 3+. So the alcohol got oxidized, the chromium got reduced. It went from chromium +6 to chromium +3. But the mechanism for this, that's inorganic chemistry. We don't care about that. Okay, so this is an aldehyde now, but that's not what we said the final product was going to be. We said that the final product for the oxidation of a primary alcohol was a carboxylic acid, so we need more steps in the mechanism. All right, so picking up where we left off, right now we have this aldehyde, right? We have this aldehyde. We know that we can write a resonance structure for an aldehyde that puts negative charge on the oxygen and positive charge on the carbon. And so what this is saying is that the carbon of an aldehyde is an electrophile. It is electron deficient. It's electron poor. It can be attacked by nucleophiles. And one of the nucleophiles that we have in this Jones reagent is water. So that's what happens next. So we're finishing up this mechanism, writing the steps, showing how this aldehyde gets converted to a carboxylic acid. All right, so we've gone from an alcohol to an aldehyde. We've gone from an alcohol to an aldehyde, and now we're going to go from the aldehyde to the carboxylic acid. Okay, so water has attacked. Now we have a lot of fiddling and diddling with protons once again, right? This proton falls off. It goes off into the solution. It's never heard from again. But there are a lot of protons in the solution. One of them is going to pop on here on this oxygen atom. Instead of writing all of those steps, I'm going to use this symbol plus minus H plus. That means take away a proton from somewhere and bring a proton back elsewhere in the molecule. So this proton falls off, goes off into the solution. It's never heard from again. But we have a lot of other protons in the solution, and one of them pops on here. And just to repeat, just to belabor the point, if this proton is Fred, this is not Fred here. This is Sally. This is Mary. This is somebody else. And so what we've created now is a special kind of alcohol. Right? This aldehyde underwent attack by water under acidic conditions, and now it's created another alcohol, but it's an alcohol with two OH groups on the same carbon. This enters into another cycle of Jones oxidation. So in other words, more chromium trioxide, more sulfuric acid, more water, all of that is in there. All of these steps happen again, but now with this special alcohol here. Okay, so now we have something that looks like this. See that guy? See what we wrote previously? It's comparable. It's all of the same mechanistic steps. And now, last step is this carbon bonded to this oxygen here has a proton on it. And so water comes in, removes that proton. These electrons collapse in here, and this oxygen chromium bond breaks. And voila, there's our carboxylic acid final product plus hydronium ion plus this CR03H minus species. It's just this, it's just a replay of this all over again. So now we see that this mechanism explains why a primary alcohol gets oxidized all the way up to a carboxylic acid, because it first becomes this aldehyde, and then it reacts with water under these acidic conditions to form a new alcohol. And then that new alcohol undergoes a second round of oxidation to form the carboxylic acid. Okay, so next time we'll talk about the mechanism for the oxidation of the secondary alcohol.